Okay, last lecture we were looking at deriving the velocity profile in channel flow. This was for laminar channel flow. And with that solution, we ended up with a parabolic profile that went from the bottom wall here to the top wall up here. And today, now we're going to move on to laminar pipe flow and derive the velocity profile distribution. The idea will be quite similar, but we'll work through it anyway. So here you have an image of a pipe flow. You can see that we have some fluid element here, this sort of salmon-colored element. And we have a pressure gradient where P1 is greater than P2, and our element has some length L. And after some time, it's distorted and moved downstream. And if we have sort of a velocity profile that's kind of assumed here, we know that if we have fully developed flow, that the velocity profile will be exactly the same everywhere along our pipe. We also know that the pressure drop that we'll have, the delta P over L, is going to be equal to a constant. So remember, that's what these are, what our ideas of fully developed flow is. So if we have, say, anything like the velocity as a function of x, the derivative with respect to our x direction, that's going to be equal to 0. So that is, the velocity profile does not change as we go downstream. We just want to make a couple of comments. Now that we are in a radial coordinate system, actually a cylindrical coordinate system, so if we look at our pipe, we have the x coordinate, and then here in this direction here, this is the radial coordinate. And then, of course, if we look at it from looking down the x-axis, then our radial coordinate goes out like this, r, and then actually there's an azimuthal component, theta, and then we'll say the total radius is going to be big R as we work with this. Okay, so let's take a quick look at the deriving this, and we're going to start from, on the previous slide, our fluid element. So our fluid element, we can go, here we have our axis. So again, this is the radial direction, R moving away from the axis, and we'll call the total distance again here from the center to the outer wall big R. And this, we're looking here at the forces that are acting on it. So we have the pressure on the left-hand side, the right-hand side. And since now, if you think about this, the wall is continuous. So we don't have separate walls, but it's continuous. So we only write down the shear stress times the area on one side of our element, which is acting against the force of the fluid moving from left to right. So let's kind of get right to our derivation. So I've tried to re-sketch this out again. Just a reminder, this is laminar pipe flow, and we have our streamlines that I've sketched in here. Just to remind you that these streamlines are going to be roughly parallel, and so since they're parallel, there's not going to be a pressure gradient in the radial direction going across the streamlines. There's only going to be a pressure gradient that's going to exist in the streamwise direction. That is, there's going to be a pressure gradient going from left to right. This is our P1 and our P2 in our previous sketch. A few more definitions. D is going to be the total diameter, and then again, R is going to be the total radius. The cross-sectional area will be noted here as our area if we cut the pipe in half. And then we'll also talk about the wetted perimeter. So the wetted perimeter is going to be the perimeter going around the outside of the pipe that would be in contact with the fluid. Our assumptions, we're going to have steady, incompressible, fully developed flow. And in this case, just like before, the momentum flux in is going to be equal to the momentum flux out. And so here I've written down the equations for that. This is just the momentum flux in equals the momentum flux out. And as a result, in our total integral momentum equation, these cancel out. And so since it's steady, we're simply left with a balance where we say that the sum of the forces in the x direction are going to be equal to the surface forces, sum of the forces, surface forces in the x direction, and they should all be equal to 0. because there's no momentum flux in or out, and it's steady. So if we take a little slice in our little fluid element slice like we did in the PowerPoint slide, and then I'm going to bring it down here and look at this force balance on it, then our element has the pressure acting on both the left and the right sides, and the pressure on side 1 is going to be times the area will be that force, and then on the right hand side we'll have some additional pressure, delta P, times our cross-sectional area, and it's going to be acting over some distance here that we called L. And the areas, so the cross-sectional area is again this area that we looked at here that's associated with the circumference, and then the cross-sectional area where the flow comes through. So that's our cross-sectional area. But we're also going to have an area along the wall of the pipe. And that area along the wall of the pipe is going to be equal to the perimeter times some length, this length L of our element. So it kind of goes out around like this. And so that's this area that we have along the outside. So the area along the wall, we'll call this tau, is going to be acting on that area, is going to be the perimeter times that length, and then the pressure forces are going to be acting on the cross-sectional area, or just pi r squared, depending on where we are. And the area along the wall is going to be that wetted perimeter, which is 2 pi r times the length L that we have there. Okay, so given that we have our forces set up, we can take this balance. Again, this is done with a Taylor series expansion, just like last class. And we see that we have the pressure times the air times the cross-sectional area minus the pressure times the cross-sectional area, so those cancel out, but we're left with a minus dP times the cross-sectional area, so minus dP times the cross-sectional area, minus, we'll see here, the shear stress times the area that the shear stress is acting over, which is now going to be the wall area, which, if you recall, the wall area is our perimeter times the length of that element. And that's all equal to 0. And so we can kind of think about how this might be simplified a little bit more. So we have minus dP times the cross-sectional area, which is going to be pi r squared, minus tau times the area along the wall. Again, this is where the fluid is interacting with the friction at the wall. That's our shear stress. And so that's going to be 2 pi RL, and that's all equal to 0. Well, our pi's are going to cancel out. One of our r's is going to cancel out here. And we're left with minus dP times r minus 2 tau L equal to r. And we can rearrange this a little bit and say that dP, so we'll dP r is equal to 2 tau L, or dP over L is going to be equal to, sorry, there's a minus sign that I left out. I'm moving it over. dP over L is going to be equal to minus 2 tau over R. And this is, if we kind of think about this as our pressure drop over some distance L. Remember, we were looking at in the pipe entry length, we had an entry length that kind of came down non-linearly, and then the curve went straight. So this is some length L along the pipe, and let's say that's the length X along the pipe as we're moving along. And then we have our entry length here, LE, where we have this nonlinear decrease of the pressure, and then over here where it's fully developed region, that's where we have this very linear decrease. So delta P over L. And what is that linear increase? It's actually minus 2 over tau over R. And this is, the way we've written this here, can be written for any small element in our fluid. And it's we can see that if we write it at the wall, so we could say here at the wall, and we just look at the right-hand side of the equation, we know that we have it's minus 2 tau over r. Well, at the wall, we'll have minus 2 times tau at the wall divided by the radius. So this is kind of like saying that the shear stress at some radius r is going to be equal to tau at the wall times r over r. So all I've done is just substituted capital R here, and now we can see how we might expect the shear stress to vary with distance from the center of the pipe. So if our pipe looks like this, and this is the center of our pipe, we have the shear stress tau wall over here, then our shear stress is going to increase linearly from 0 at the center of the pipe to at the wall. Then we can substitute here capital R at the wall, so we'll have tau wall at the wall. So actually our shear stress then is going to be symmetric about the center, and we can think of the shear stress as increasing linearly from the wall. Increasing linearly from the center to the wall. Okay, now that we understand the shear stress a little bit better, we can rewrite our equation that we had there just a second ago. So we have that dP over L is equal to minus 2, and this is our tau over R. And what we can do is go ahead and make a couple of changes here. So dP over L, this is actually not, this can be written in terms of a differential as dP dx. Okay, so just dP dx is equal to minus 2 over R times tau. Okay, and tau, that's our shear stress. And we know that the shear stress is equal to mu times du dr. And this is similar to what we had in the channel flow case, where for the channel it was mu du dy. But now our coordinate that is normal to the wall is r, the radial coordinate in our cylindrical coordinate system. So we can substitute this back up in here, and so we'll have then minus 2 times mu over r times du dr, and then we'll have that's all going to be equal to our dP dx. And we'll remind ourselves again that the pressure gradient here is equal to a constant, and since that, in that case, then we can go ahead and let's call this equation star. We will separate and integrate equation star. And if we do that, we end up with, let's say, du dr to start out with. That's going to be equal to minus r over 2 mu times dP dx. And then du is going to be equal to minus r over 2 mu dP dx times dr. Again, remembering that mu is our dynamic viscosity, which we should have remembered from before. Now, given what we have here, we can go ahead and integrate. So we'll go ahead and integrate, and if we do this, we can integrate one time, and we're going to integrate it from the from the center to the wall. So we'll have that u now of r is going to be equal to minus, and this integral that we have here, so all of this except for the r, we can move that over here, and all of the rest of it, it's a constant. We'll have minus 1 over 2 mu dP dx r dr. So, we'll do the actual integral. 1 over 2 mu dP dx, and then we'll have r squared over 2 plus our integration constant. So it's a pretty straightforward integral. And just like before, we're going to have to go ahead and apply our boundary conditions. So I'm going to apply the boundary condition to get C1. And our boundary condition, this is a first order differential equation, so we only have one boundary condition and one constant that we have to get here. Our boundary condition is that the u at the wall, so u at r equal big R, is going to be equal to 0. So we can substitute that in as u of 0 is equal to minus 1 over 2 mu dp dx times 0 squared over 2 plus c1, and that all is equal to 0. So C1 that we have here now is going to be, we're not evaluating it at 0, we're evaluating it at R, capital R. So then C1 is equal to 1 over 2 mu dp dx times R squared, pardon me, over 2. So that gives us our constant, our integration constant, and then the solution, u of r, is equal to, we're going to go ahead and substitute this back into here. Our solution is going to be minus 1 over 4 mu dp dx times r squared plus 1 over 4 mu dp dx times big R squared over 2. And then we can do a quick simplification, and we end up with 1 over 4 mu times dp dx. So we're just going to pull these guys out, and then times, there's no R squared there. That's the 4 there. Times R squared, this is our big R squared that's here, minus the little r squared. So that's our solution, and sometimes you'll see this modified just a little bit. We can pull out the capital R. So we say u of r is equal to r squared over 4 mu times dp dx. And if we pull out this r squared here, that means that we have to basically divide by r squared inside the parentheses. So we get 1 minus r squared, little r squared over big R squared. So if you distribute that r again back into here, you'll see you have r squared minus big R squared minus little r squared. So that's our solution for the velocity profile inside a laminar pipe flow. So this is our laminar pipe flow velocity profile. And it's the same everywhere in the pipe because it's a fully developed pipe flow. And we can notice, just like with the channel flow, this is a function of r squared, so capital R squared is a constant, and it varies. This is like a parabola, and this allows us to kind of better understand what's going on with our velocities inside of a pipe. Now we can also do a few other important calculations that are used with pipe flow. We can calculate the centerline velocity. So centerline velocity, we'll call that V sub c. And that's just going to be evaluating the velocity profile at the center line. So the u at r equals 0 is equal to the velocity at the center line. And that's going to be just going back up here and putting in a 0 for the radius, which will give us what's on the left-hand side here. So then I'll bring that down. So that's going to be equal to r squared over 4 mu times dp dx. So that's our center line velocity. And another important quantity that I would like you to be able to calculate, sorry, move down, is the flow rates. So so let's compute the flow rate through the pipe. And all that's going to be, so I'll call that Q. Our flow rate is going to be the integral of that velocity over the area. So Q is going to be equal to the integral of our velocity U times dA, and I'll call this a little r, because what we're going to do, and hopefully I can make this work here, I have my circle here, we're going to have this little annulus. We'll try to make that in the middle. We're going to be doing this integration, and it's still not wanting to find its spot. There we go. We'll have an annulus that we're going to deal with here. Oops. Okay, so we'll have this annulus that's here that we're going to be integrating over. So we'll have many of these as we go outward, and so we'll start out at the center, we'll move out in the radial direction, and this little annulus is some element dr. It's like when we just simply, like in calculus, when you're integrating to determine the area of a circle. So the area, this that we have here, this, we'll call it dAr, is going to be equal to our circumference around the outside times r dr. So we'll have 2 pi r dr. So we can substitute that back into our flow rate equation. So we'll do the integral from 0 to big R that we have here, the u of r, and then 2 pi r dr. So what do we do for the u of r? Well, that means we can just go ahead and substitute our equation that we have right here in either of the forms that we're interested in looking at. So let's go ahead and do that. So if we substitute in, we have Q equal to integral from 0 to r, and the original equation that we have here, let's just use the any one of these, but let's use r squared over 4 pi dp dx. So r squared over 4 mu dp dx. So that's, I'm just copying this here, this over here, r squared over 4 mu dp dx times 1 minus r squared over r squared. It's 1 minus r squared over r squared. And then we have to multiply that by our 2 pi r dr. And there's a bunch of this that's just a constant. So this here is all a constant, and 2 pi is a constant. So we can write this out in front as far as that goes. So we'll have 2 pi times r squared over 4 mu, and then we'll multiply that by dp dx, and then we'll be left with r minus r cubed over big R squared dr. So we have 2 pi big R squared over 4 mu times dp dx, r minus r cubed over r squared. And we can integrate that pretty quickly so that the 2 becomes, divide 4 by 2. And we end up with pi, and then we'll have the big R squared divided by 2 mu times dp dx. And our integral is r cubed over, r squared over 2. We only have a single r there. We're going to integrate this r squared over 2, and then minus r to the 4th over 4 big R squared. And then we'll evaluate that from 0 to r. Because this was back over here, this is our integral 0 to r. So let's go ahead and substitute capital R into the equation. And if we do that, we end up with Q pi r squared over 2 mu dp dx, big R squared over 2 minus big R to the fourth over 4r squared. And here, this cancels out with this, so 4 divided by 2 there. And then we're left with the following. So we'll have equal to pi r squared over 2 mu dp dx. So we have r squared over 2 minus r squared over 4. So that's 2 over 4 minus 1 over 4. So we end up with r squared over 4. And in total then, you can see that we have q. So we have equal to pi. We have 2r squared, so that's r to the fourth power. And then in the denominator, we'll have divided by 8 mu. Because we have the 2 and the 4 that we have there. So there's going to be divided by 8 mu times our pressure drop that we have here, which is dp dx. So that's now what we have as our flow rate, which is a very, very important quantity that we look at here in pipe flow problems. But let's talk about it a little bit. Another way that we can also write this just a slightly bit different is we can think about that dp dx as, instead of being a derivative, we can think of it as the pressure drop over some length of the pipe. Oops. So over 8 mu times dp, say, over L. So let's think about this in terms of a physics point of view. What affects the flow rate? So what affects flow rate? Q. Well, we see here R is really strong. So R has a strong effect on Q. So if we, it has a quadratic influence on the flow rate. So very, very small radii will result in very, very small flow rates, but much bigger, and you'll increment bigger, you'll get a much, much bigger flow rate. So the strongest, pardon me, the strongest flow rate effect is the radius. So an increase, increase in R leads to a big increase in Q. We can now look at the pressure drop. So the larger the pressure drop, the larger the flow rate, and that makes sense. So if I have my pipe and I have P1 and P2, these are like forces on the left-hand side and the right-hand side. If I increase this pressure drop, that means there's going to be more force to push through the pipe, and so we'll have a higher flow rate. So Q increases with increases in the pressure drop that's applied to the pipe. And that makes sense. What acts against the flow rate? Well, if the longer the pipe is, so as L increases, Q decreases. Why is that? Because then we're going to have more friction along the wall, and that's going to act to retard the flow. And then similarly, mu, as the viscosity increases, the flow rate decreases. So this is a nice example of how flow rate is affected by these critical parameters: the radius, the pressure drop, the length, and the viscosity. And this is going to be, this is actually quite important, and I'd like you guys to remember that for probably a quiz that I'll try to give you sometime relatively soon. Now, we've been talking mostly so far about laminar flows, and we know now that a laminar pipe flow we have here between two walls, we've just derived the fact that the laminar pipe flow is going to have this nice, beautiful quadratic profile. It's a parabola. But what about turbulent flow? Turbulent flow is more complicated. So we cannot get the analytical solution for that, but what we can do is run experiments to understand what they would look like a little bit better. So I'm going to move back to the PowerPoint presentation and kind of go through some of these slides to understand better what that's going to look like. So just a reminder here, so this is kind of a summary. This shows over here on the left side our shear stress distribution that's linear, starting from 0 and going to tau w at the wall. It also shows our parabolic velocity profile and compares it to the inviscid idealized profile that we have. The other quick comment that I'll make for laminar flows is you could do the same derivation and include the effects of gravity. Remember, thus far we've been dealing with a horizontal pipe, and if we don't deal with the horizontal pipe, then we have to add this term here to our derivation. And what that ends up doing is making our shear stress. Remember before, for a horizontal pipe, this was not part of the force balance. So we've added the weight of the fluid acting in the gravitational direction as our buoyancy force. So we just don't have surface forces. And so this modifies this a little bit. We still have the 2 tau over r just like we had before, but now we've added this buoyancy term. And then the modification to the flow rate looks like this. Okay, so now, turbulent flows. So we talked already a little bit about turbulent flows when we were discussing Sir Osborne Reynolds' experiments. And here what we have is how do we deal a little bit with turbulence. So usually when we've derived things for a laminar flow, we just talk about u as the velocity. But in turbulent flow, the velocity is very complicated. You can see this time trace here that is very almost chaotic appearing. It is deterministic, but it's very hard to determine, and we can't typically do it analytically. So what we typically do is break our flow, and so this is this velocity time trace. We break it up into a mean, u bar, and then some fluctuation from the mean that we call u prime. And what we'll do is we average, to get this u bar, the mean, we average over time. And that's what this equation down here is showing us, where if we take the velocity at any point in space, so any x, y, and z point in space, and we average it. So u bar is our time average. It's our time average. And it's going to be equal to 1 over t, the averaging time period, times the integral from the start time to the end time of the velocity in that time trace. And so that is one of the key points that we deal with turbulent flow. We can't have an instantaneous velocity. It's very difficult for us to deal with that analytically or even experimentally. So typically what we do is we take these fluctuations that are associated with turbulent eddies. So each of these fluctuations that you see here are associated with eddies that are going past some sort of a probe, say a hot wire anemometer probe, that are blowing across at some velocity u, and then mean velocity, and then these eddies are causing fluctuations that have a little higher momentum or a little lower momentum in the fluid. In fact, the way you can think of this is, say we have a mean velocity profile. So this is, and we'll just look at a wall for a second. So say u as a function of y going away from a wall. Say our mean velocity looks something like this. Then on average, and let's put a bar over it so that you can remember that it's the average velocity, turbulent eddies are going to take momentum from up here, this high-speed fluid, and bring it down lower. And at the same time, eddies are going to take these low-speed fluid elements and move them to some other part of the flow. And as that's happening, that is what's causing these fluctuations about the mean over here in this time trace. So I kind of would like you to think about it in that way. We're having mixing going on. And it's not just mixing of things like dye. If I put some colored dye into my flow, the dye would be mixing around, but also momentum. And that mixing of momentum tends to smear out gradients in the flow. So if you have in a turbulent flow, let's move over here to the right-hand side. Then say we have, say, Y and C. Now this is C is a concentration of dye. Think of it as blue dye or something, concentration of dye. So then maybe the concentration looks like this. I have a low concentration, and then boop, I have a high concentration. This is, I put blue dye here, and up here there's let's just say for the moment there's no dye. So this is blue over, clear dye over blue dye. And if all we had were effects of molecular effects like in laminar flow, then very slowly these gradients between the dye would slowly change, and the blue would slowly move up into the area above. But for a turbulent flow, the eddies act to really mix up this interface and very quickly degrade this gradient so that it mixes much more rapidly. So we want to think of turbulence as mixing and degrading gradients in the flow field, whether it's momentum or other scalars. And so that is going to make a big difference in what our flow looks like. So here, this is a plot on the right-hand side of the mean velocity. So on this right here, this is mean velocity profile. And so how does that look compared to the laminar profile? So this is our centerline velocity that we have. And that, at the wall, of course, we still have a 0, the no-slip condition. But you can see that very rapidly, instead of a slow parabolic increase towards velocity centerline, we have a really rapid increase, and then it's relatively constant here. And that's because turbulence eddies are acting to mix the fluid and destroy the gradients, and that means that the velocity gradients are being mixed out. So if we have a really strong, almost constant velocity near the center of the pipe, it still has to go to the no-slip condition. It means we're going to have a sharp gradient at the wall that remains. It has to, because it has to go to the no-slip condition. And since we know that the shear stress in laminar flows goes like the gradient, du dy, and at the wall, we still have the viscous effects that are important. So the shear stress at the wall is still going to be proportional to that velocity gradient. And that means that the shear stress of turbulent flows is very large. So we'll see here that the shear stress at the wall for turbulent flows is much greater than the shear stress at the wall for a laminar flow. And over here on the left-hand side, this is kind of looking at the different parts of a pipe that have different aspects of the shear stress. So here, we still have a linear shear stress distribution that goes from 0 at the center line to tau wall at the wall. But what we want to note is that near the wall, we're going to be dominated by laminar processes. That's going to be the molecular process. But as we get away from the wall, that means that shear stresses are going to be dominated by the fluctuations in the turbulent flow. So how does that affect the velocity profile? Well, I told you it flattens it out, and so we have some parameterizations that we use for this. One is called the law of the wall. It's a logarithmic profile, and we use it actually both in boundary layers and in pipe flow, but we'll introduce it here. We have this thing that we're calling U star, and you know, U star is what we call the friction velocity. And the friction velocity, so U star, is equal to the square root of tau wall over rho. Sometimes this is called a kinematic wall shear stress. Kinematic wall shear stress. Because we divide it by, it's a shear stress, but we divide it by the density, meaning that the velocity units or the units of U star are just velocity. There's no density in it. So this is the characteristic velocity for our flow at the wall. And so we usually do some non-dimensionalizing of our velocity profiles by this characteristic wall velocity, or this characteristic kinematic wall shear stress. Again, this U star is sometimes called the friction velocity. and in some places you'll see it called U tau as well. So some places call it U star, some places call it U tau, and it's relatively important. And what we have is experimental data that will allow us to show what the velocity profile looks like. So in this case, this is just to note, we have a log scale here on the x-axis and a linear scale on the y-axis. And so near the wall in this scale, we have a profile that looks a little bit like this, and the experimental data follow it very nicely. But then as we move away from the wall on this scale, the data seem to follow this line that doesn't have a curvature to it in log space. And so we have actually two different equations that we use. One for very, very close to the wall, and you can see that it's non-dimensionalized. Y is the distance away from the wall, distance from wall. Yeah, have your wall here. Call that the distance away from the wall. And y plus is a non-dimensional distance that's away from the wall. Sometimes you'll hear it called, and that's going to be the y times u star divided by nu. You can do classical dimensional analysis like you've done with Buckingham pi to determine that y plus is their correct wall normal dimension. So that's what we're going to have here. So if we look at those two curves and you just fit it with experimental data, then the linear curve that we have, this guy, that's our equation 8.30, so 8.30 that's in there, is our law, part of our law of the wall. And then down near the wall, we have this equation where u over u star is equal to y u star over nu, and that's this over here. And just like y plus is sometimes called y u star over nu, sometimes you'll see people call u plus equal simply y u star, this guy on the left-hand side. U plus is often defined as u bar, or the mean velocity at some height y, divided by u star. So sometimes you'll see these curves as written as u plus versus y plus. Okay, so that's a relatively complicated format for the near wall velocity profile in turbulent flows. Oftentimes we simplify it greatly, and we go directly to just using a power law profile, which is much, much easier. So in such a case, as we've written down here, the velocity at any radius r divided by the centerline velocity, so u over v centerline, so centerline velocity, is equal to 1 minus r over r to some power, 1 over n. And on the right, excuse me, on the right-hand side, you have examples of the different values of the exponent 1 over n. So n equal here 6, 8, and 10. And you can see as n increases, we have a stronger gradient at the wall and flatter profile. And you can see here also nicely the comparison between the laminar profile and the turbulent profiles. And this is something that's really important. Being able to sketch a laminar profile and a turbulent profile on the same curve, and this is a non-dimensionalized axis. So r over r, where big R is the total radius, divided by u over vc. So here we're starting at r equals 0, so that's the center of the pipe where the velocity is maximum vc, and then out here, this is the wall. So of course the velocity has to go to 0 at the wall. So being able to sketch this pipe flow velocity profile is very important. Okay, so that kind of finishes up what I wanted to talk about today. The next thing we're going to do, and I know today has been quite theoretical. The most important things is that you understand where it's been coming from, and that you're able to understand and apply these velocity profile equations, understand the shear stress, understand the flow rates and the physics of the pressure drop with relationship to entry length. It's also important that you understand the interaction between shear stress and the pressure drop. The next thing we're going to do is we're going to take what we've learned here and integrate it with the energy equation and apply that to pipe flow calculations. And this will be what we're going to use as what's called the classical Moody diagram type problems, where we're going to determine the pressure drop, flow rates in real pipes, applying the energy equation. So this is very applied and practical, and hopefully will not be too bad for you guys. Thank you very much, and we'll see you at the next lecture.